today and in this Greece meeting. So we are starting with the Star Sessions Advances in Computing, Retrievals and Products. I'm chairing Igor Tomajic and helping Benefit Bremer and Jagdish Prajapati in taking the notes. Thanks. So we are starting first with the keynote presentations from Cristina González-Haro on exploring new cloud detection algorithms for remote sensing SST observations using data-driven approach and the multifractal theory of turbulence. Please.
Okay, thank you, Igor. So good afternoon, everyone. Thank you for being here, and you had your lunch pause. Hopefully you have a nice coffee and you will be waking all the presentation. So let me first, oh, someone is missing here. They the other co-authors, I don't know what happened. Okay. they just disappear. Okay, don't worry. So I would like just to introduce a few seconds to present the co-authors, even if they disappear from there. But this work, the main contributor is Aina García-Espriu, who is making, I mean, she's doing her PhD. And so she is the real expert on the data-driven approach, together with Fernando Aguilar from the Instituto de Física de Cantabria. Both of us, we are co-advising Aina. And then we have the contribution of two more people that you may already know. So this is Jordi Isern and Antonio Turiel from ICM. And they are the experts on turbulent and all the framework that I will explain you. And so today it's me presenting. You will have to deal with me, and I hope I'm just an ocean remote sensing engineer that has dived into the physical oceanography for the past few years. And I'm your opportunity to get something understand about the multifractal theory that I will explain you in the first part of the presentation, just to give you some key points to understand the proposed that our approach to try to improve the cloud mask for SST infrared. So I think in this community we don't need to do a slide like that in order to explain the motivation of this work. I would like just to quote Sally Wood in these days, who said that cloud masking during our session on polar regions, that said cloud masking is not only relevant for polar regions, and it is a global problem. You may know that it's made relevant. So here, as an example to illustrate this, we have Sentinel-3 level 2P image, and if we just back and forth, we have here the mask, and you can see that some problems may arise with this cloud mask. And it is really important as well, especially for the upwelling regions, as Christo showed yesterday, where we have these huge gradients in the coastal zones, and then we may have some problems masking out these SST observations. So now I will just devote a few slides talking about the multifractal theory, the exponential singularity, and so on. This is something that, if you have attended to other Greece science meetings, you already have seen, but I need to go through this. So coarse grain gradient at the small scales of temperature in this case can be written as this function. This is like a convolution filter, where this G function is a filter that is normalized, positive function, and that decays fast to zero. So at small scales, these gradients are dominated by this term, a term that will be depending on this G function. But the interesting thing is that they scale, or they are proportional to the scale up to this H that we call, I mean, this is the singularity exponent. And the mathematical meaning of this exponent is that if this value is between an integer n or n plus 1, that means that the gradient is derivable n times, but not n plus 1. So this would be the mathematical terminology and the meaning. But if we take sea surface temperature images, we may recall this expression that we just saw. what we propose is to use this singularity exponent, which are these. This is an SST. This is modeling. This is not remote sensing. This is the outputs of the model in the California upwelling region, and these are the exponents that we obtain. These are this kind of we call it familiar spaghettis. So, and that give us we propose to use this as a measure of intensity of the front. So it's giving us the spatial distribution of the fronts, and as well the intensity of the fronts, meaning where the strongest fronts correspond to the smaller exponents, which are the white values here in the image. Okay. Now if we move to introduce the singularity spectrum, if we now take the domain of the flow and divide it into subsets according to that exponent, we measure the extension of each subset of that we divided using the fractal dimension of the set. So, and this is what it means, this expression here. And this is what we call the singularity spectra that would have this a continuous function that gives us the spread of those points with the same singularity exponent. So we plot it at the singularity here in the horizontal axis. This is the exponent singularity, and that would be the singularity expression. So what it means, what it's giving us, the oceanographic interpretation for that would be that this gives us the intensity of the front, having, as we said before, the smaller exponent singularity are the most intense front, and this will give us the front extension. This value D would correspond to the maximum fractal dimension that in our case, since we are dealing with images, would be 2, okay? And so since there are multiple exponents, we say that the flow is multifractal. So, and this maybe you have to believe me, but you can go deep into the literature. Since the turbulent cascade implies that this singularity exponent, for me this is a concave. Now I think that this is a convex, but when I studied this has this concave shape. Okay. And so how do we compute this singularity spectrum? So according to Friis, the distribution or the probability density function or the histogram, we call it like that, of this exponent is proportional to the scale up to this D, which is the maximum fractal dimension, and the singularity exponent. So in the group, they have devoted quite a few years to optimize the computation of the singularity exponent and this DX. So what I want like to state here, and this is a key component for what is coming after that, is that so from the distributions, so once we have the singularity exponents available, we can compute the singularity spectrum from the histograms of H. But what is important is that if this singularity exponent has this concave function, the distribution would need as well to be unimodal. So we don't expect to have two modes. Okay, this is the key point that we would need that. We will recall that later. Another key aspect is that the optimized estimation of the singularity exponents imply a global normalization. So it depends on the domain election that we select for computing this singularity exponent. And this is another key aspect. I mean, I'm just giving you the messages, the important things, so that you understand all the things that we are going to be to need later for explaining our approach. So now that we have introduced the singularity exponent, there is another key factor of the singularity spectra, that is the independence of the scale. So to illustrate that, here we have the singularity exponents at a given, at different spatial resolutions. So it will be the nominal original distributions for going to that point. And I hope you are not color blinded, because I think the election of the color, it might be not, I don't know how you see in the screen. At home, maybe they are better. But the different election of blues here indicates the different spatial resolution. So from going to the nominal spatial resolution, this here we are going, I mean, we are reducing by half. We are taking 2 pixels from 1 and then 4. And what it is important is that the resulting singularity spectra of these images are the same. So this is what you have here, okay? The only thing is that reducing the number reducing the spatial resolution, you are reducing the number we have for computing the statistics, and the error of the estimation of the singularity exponent may increase, especially in the extremes where we will have less observations. But this fact is really, it's a key factor, and that makes that this diagnostic or this singularity spectrum is well suited for comparison between different data sets at different spatial resolutions, or even comparing models with different spatial resolution. And that's what we did in the framework of the Future Fidelity Task Team a few years ago, with people here sitting in the room, with Chris Merchant and Peter Cornillon. So we assessed the capability of different level 4 data sets in order to represent these fronts, or to assess the consistency or the dynamical consistent. We were commenting in the last session. So if I'm a user and I'm interested in fronts, which product do I need to choose? So this is a powerful diagnostic to find out this key question. So here we were intercomparing. This is a level 3 AMSERI, and it's 1/4 degree. I mean, they are in order of increasing spatial resolution, and this was the result that we obtained. As you can see, some of the products have a loss of energy in some points, and that allow us to conclude that the different algorithms used in interpolation of the level 4 products are reducing this dynamical information. So you may recall this, here we introduced the median of the individual images here. The red line is the median of the AMSER2, which is closer to the theoretical expected function or behavior. And you may recall that curve because it will appear a few slides after, but we will change the color. It will be black, okay? The red will be black. But this is an important key result of that. Means that, I mean, the higher spatial resolution we show here does not mean a better dynamical representation at a given scale, okay? So we will take our microwave as a reference for our purposes later on. So coming back to the singularity exponents. Here in the image, you have the singularity exponents for the full tile as an example of Sentinel-3 level 2P, okay? And you just begin to see different features. I mean, it's kind of intuitive that the stronger fronts correspond maybe somehow some atmospheric features here. The texture is kind of different, you will see. So we may recall that the retrieve variable, the retrieve variable that we have is a mixture of the real sea surface temperature and a rescaled version somehow of the cloud temperature, okay? So since ocean and the atmosphere are turbulent fluids, they will follow the turbulent cascade, and therefore the singularity exponent on one and the other, they will have the corresponding singularity spectra. And what we are hypothesizing here is that both singularity spectra are the same. Okay, this is a strong assumption, but this is what we will assume, and I will show you later some of the results. So For this image here, we have computed singularity exponents for the full tile, okay? And then we have used, something's going on with the presentation, I don't know. It would be an arrow here, I don't know, it's something. Okay, so we use the original cloud mask given by the product, which is here. So we use the original cloud mask to split. Once we compute the singularity exponent for the full image, we split the values that are indicating C and cloud, and we compute the distribution of the exponents. And you may recall what I've introduced you before. This is the key point I told you before, is that we should expect that they are unimodal. And what we see is that some of them, I mean, the blue value would be the distribution of the cloud part of the image. The green one will be the full image, and the C will be the orange. Okay, so there was another key important factor I told you before, you may recall, is that the optimized estimation of the singularity exponent imply a global normalization. So it depends on the domain election. So here what we are showing is we have the same tile, but then we use the original mask, and we split the SST image, and we compute independently the singularity exponents. And we obtain these two distributions, okay? So let's put it in the form of the singularity spectra that I showed you before. So here, what we have our reference curve from the microwave, which is the black curve that I told you before. It will be the red, will be the black. So that one, this is our curve. This would be our reference because it's the best estimation of the theoretical singularity spectra. And so here you have, in solid lines, you will have the singularity spectra computed from this image. When we splitted the image and we separated the exponents. And the corresponding dashed line would be the separation we do, but after computing the singularity exponents for the full image. I don't know if it's clear or not. I hope it is. So here we take our image in the solid line, we take our image and we segment it before computing the singularity exponents. And in the other case, we compute the singularity exponent for the full image and we do the segmentation afterwards. Okay? And you can see that quite different appear. I mean, it's quite interesting. On one side, when we segmented that, the C in that case, it's quite close to the expected value, at least for this part of the curve, for the positive values. You can see that it's closer to the black curve. I hope you can see it. The clouds are not. So this means that the mask that we are giving, it's a good first guess for the cloud masking. Okay, in the most in the singular part, which corresponds to the stronger fronts, okay, we may have some other problems here, but this is what we have. So now that I've introduced you and all these kind of key points of the multifractal theory, I will now show you which is our objective. So our main objective is to explore data-driven approaches to improve this cloud mask. And how we will use it? We will define metrics based on this singularity spectra, and we will explore some different AI algorithms. So the final objective is to grant that the C pixels verify the energy cascade, and so they are closer to the expected behavior of the singularity spectra. Okay, this is our main goal. So, in order to do that, I'm going to present you some preliminary results. We are working on that, but the first thing we have done, this is the first proposed classification algorithm. We're given an image, an SST level 2 product. We segment this image, taking into account different regions according. We have made some tests segmenting the according to a constant value of the SST, so it would be an isothermal, or from dynamics according to their value of the exponent, singularity exponents. So once we have segmented our first mass, we take the first guess, we consider the cloud mass given, and for each segment, we swap the pixels from cloud to the sea. We reevaluate our singularity spectral that we will consider as a, we will use it to define the cost function. So this is what we want to minimize. And then we will accept or change the pixels according to the evaluation of the cost function. So I hope you are still there. So this is an infography of the cost function that we are using. So we have our reference in our target reference singularity spectra here in gray, and this is will be what we measure. So we are trying to use two different metrics according to the singularity spectrum. One would be the area under the curve with respect to the target function, and we want that to be close to zero. This is what our cost function. We're using that threshold because normally in the extremes we have some more errors determining this function, so we compute the area under the curve from a given threshold. Another method that we have used is compute the curve difference with respect to the reference curve. Okay. And so if you just arrive up to here, I will show you some preliminary results of an example of a given mask. So on the right here, we have the original mask for a given tile. And here would be what the final mask that we obtain according to the metric, which is the area under the curve. And here is what we have now in solid line would be the final singularity spectra that we have, and the dash point corresponds to the original points. So as you can see, for the C, that is our target, we have improved, especially in the positive side of the spectra. And for the negative part, okay, it did improve a bit, but not that much yet. For the other metric, for the curve difference, it's getting a bit better, but this are just preliminary results. So this is, and one of the maybe striking things here is that now the final mask is kind of more noisy or pickled, but it might be what is happening in reality. I mean, at the end, the clouds are not that homogeneous. It's not all of the pixels may be discarded here, but may happen that some of the pixels may be useful yet, and this is not as restrictive in this area here. So, and these are just preliminary results, and as a future work, so we need to define a good segmentation algorithm, and we are considering some algorithms like the mass dilatation erosion or other segmentation algorithms. And for the minimization algorithm, so we are just considering all these kind of IA algorithms, so iterative class change, that is what I showed you, some genetic algorithms, clustering, or simulated annealing. So, and just to sum up and some conclusions, we proposed a new cloud detection algorithm for infrared SST using a data-driven approach and based on the multifractal theory turbulence. So as I told you, the main idea is to use the singularity spectra of a reference SST, in that case is microwave, to define this cost function. First preliminary results, I think it's encouraging. This is a sentence we always say, but I hope I've managed to convince you that they are really encouraging. And as I said, we are now working on improving and finding the best segmentation and minimization algorithms. So to end up, if you want to keep learning about multifractal theory, I just leave you some references here, and I think this is all from my side. I might be, I don't know how many minutes I'm left, or kind of 6 minutes. Okay, that's perfect. Thank you very much for your attention.
Thank you for a very interesting talk. Yeah, we have 5 minutes, 6 minutes for questions. If anyone have some questions. Yes, Andy?
So the AMSA being your kind of reference, this is what it should really look like. Maybe slightly surprising because of the large footprint. And also, therefore, are you confident that everything in that particular spectrum is actual genuine geophysical SST variability?
Yeah, I mean, I'm the confident I can be. I mean, in the sense that from a observational perspective point, this is our best estimate. That it is the absolute truth. But yeah, we are pretty confident that it should behave as this. Yeah, according to the theory.
Yeah, I mean, I was just thinking that, you know, obviously you could look at model data.
Yeah.
And see, is there a way of distinguishing between actual geophysical flows with the right, you know, Rossby radius and
but then,
versus other things? When you said like we expect clouds to basically have similar fractal type behavior, like with my eye, I can see the difference between a cloud and a geophysical, you know, sub-mesoscale eddy or something. So.
Yeah, so in that work here, particularly, and the work that I showed you, the image that I showed you, that it was model output. I mean, we have been studied that from the observation and modeling perspective, okay? And we may think that the models are perfect, but they have other limitations. So and the point is that this framework allows us as well to compare the models. So what I'm trying to say here is that I completely agree that the observations have some problems, but the models have others. So we need to play with the interplay indeed. I don't know if this answers your question.
It means there's more work to do.
Of course, we it means that, and we are working on that. But yeah, sure.
Okay, we have one online question. Sorry, just from Jorge. Jorge, please.
Oh, thank you. Thank you for that really nice presentation. And in terms of the future, I was thinking is would it help in terms of applications of the cloud masking to look at areas where we might have some in situ validation? You know, I'm specifically thinking of sail drone and do some comparisons directly. Would that help?
Jorge, I don't know if I get, because I couldn't hear properly, but what you are suggesting, if it's studying somehow if the sail drone measurement will help to somehow to the conclusions. I don't know what would you were proposing. I mean, I just understood something about the sail drone observations, but.
Yeah, just do a direct comparison, you know, between sail drone gradients and what you derive using the methodology. Would that, I mean, because I mean there are sail drone deployments in the Mediterranean.
Yeah, but you mean taking? I mean, it would help, but the point, I guess, that the sail drone are a long track measurement somehow, so you cannot retrieve the. I mean, it would be it would be a fractal dimension 1 if you are in a line, and it may help to somehow it would be interesting to guess if somehow especially for validating the gradient, it might help, but we will have different topology of measurements, I guess.
Yeah, I see what you're saying. So yeah, well, this is really exciting. Thank you.
Thank you, Jorge.
Okay, maybe one, I don't know, quick question.
I can ask it quickly.
quick.
So one comment is I think it would also be useful to as well as having the simulated ocean, to have the simulated atmosphere with the clouds and the simulated radiation transfer and really check how it works end to end. So very interested to try and make that happen with you. But also, I mean, there are different sorts of clouds. I'm not sure that cumulus and stratus and cirrus and contrail cirrus will have similar spectra. And is that going to confuse things when you try to apply this more generally?
Can you reformulate your question? I'm not sure. If the different clouds will be, I mean, you are suggesting that it might be a stronger hypothesis that they have the same singularity spectra, is that?
I think surely they will have different singularity spectra. And if you've got multiple things going on, you're not just separating two things perhaps, but many spectra.
For sure, that's why the shape is changing. But what we are assuming is that if we would, in an imaginary world that we are able to split the both fluids, they should converge to the same singularity spectra. I mean, yeah. I mean, it would be different. Yeah.
Okay, thank you. I think we need to continue with our next speaker, Paolo Cipollini, making the best even better, expected improvements in sea surface temperature from advanced ASLSTR on Sentinel-3 NG Optical. Please. It's better. It's already better.
Okay. Good afternoon, everyone, and it's a great pleasure to be here with the GHRSST community to talk about our next fundamental mission for sea surface temperature, or I should rather say aquatic surface temperature, because we will improve the resolution, so we think we will even get to cover a larger domain for inland waters and also improve the coastal applications. So I'm going to tell you very quickly about how we are making what is the best sensor, perhaps a bit cheeky, I call it the best sensor for the SST, the ASLSTR series, even better with the next generation that goes on Sentinel-3. So just to put things in context, I'm sure most of you will be aware that the current Sentinel-3 mission evolves into two separate missions. So the topography payload that goes on Sentinel-3 NG Topo, whereas the optical payload, which includes the color sensor, OLCI, or the evolution of OLCI, and the evolution of ASLSTR goes on Sentinel-3 NG Optical, which from the point of view of science is followed by myself and my colleague Simon Proud, who was here with you earlier this week. And for Sentinel-3 Next Generation Optical, the objectives are to continue the observations and make them even better. So it will be enhanced continuity of observation of the optical component of the current Sentinel-3 mission. Again, the topographic component goes on different satellites, Sentinel-3 Next Generation Topography, or NGT as it's called. In particular, for this mission, NGO, S3 NGO, we look at the continuation and improvement of OLCI and ASLSTR. So those instruments that provide essential data to the Copernicus services, enabling a large number of downstream applications. And it is, by definition and philosophy, the wide swath mission at moderate or mid-resolution, providing frequent observations over the oceans, long-term, with consistent quality, very high level of availability, but also over the other domains. So it covers a lot of land applications. And indeed, with the next generation, we will also improve operational products like AOD and fire products that cater for the atmospheric services. And also, I should say, it's not mentioned there, but I should mention it, the emergency services. Now, let's focus on the oceanic domain and the sea surface temperature. It's obvious to you all, to this community, of course, and to many users that data like those that you see on this simple plot, simple map, which is a combination of ASLSTR-A and ASLSTR-B sea surface temperatures in the Agulhas current. These are the workhorse of a lot of operational oceanography and many applications. So how are we going to make ASLSTR better? I'll show you a table with the key requirements with a caveat. We've highlighted here in green, and I apologize that reporting from the market window part of the text is covered, but those things highlighted in green should be the improvement, the obvious improvements with respect to the ASLSTR. But the numbers on the right-hand side are all TBC and the subject of discussion. And in fact, even earlier on this week, Simon might have already told you some further improvement that we want to make to those numbers. The basic idea is that we will do at least as well as the current ASLSTR at a high resolution, because you see, we go to 500 meters even for the thermal channels, and for some of the solar channels, we are targeting 250 meters, and the industry are really looking whether they can achieve that. If we're possible, we will improve the performance, but there's some trade-offs to be done on those numbers over there. But I really would like to stress the fact that we are adding 3 channels. The one in the blue, channel 1A, is very important, especially for aerosol applications. The one in 4A can be used as a proxy again to derive atmospheric corrections that in turn should benefit our the data that we get from the visible sensor. And crucial for sea surface temperature observations is this new channel at 8.70 micron. This is a slide that Simon has already shown to you earlier this week. But it is crucial because we have had a science study, NGS ASLSTR, led by John here. And this study has looked at the impact of these additional channels, in particular this channel 8.7 micron via simulations. And it is very beneficial. In particular, when you look at the numbers, it will halve the uncertainty on the nadir-only daytime retrieval. It almost brings it in line. It certainly brings it so much closer to the other retrievals that we got for the dual view in day and for the nighttime retrievals. The effects on the nighttime retrievals are minimal. There's a tiny effect even on the dual view daytime uncertainty, but in particular, it is the nadir-only daytime retrieval which improves so dramatically. We also looked at the channel at 4.5 nanometer, a possible channel there, but the impact is negligible, and I don't think we will add it in the end. We have for Sentinel-3 NGO a strong mandate from the EC to increase the synergy of the 2 instruments, of the 2 souls of this large mission, which should enable improved applications. So we will generate an improved L1C product where we map the ASLSTR channels onto the ORCHI grid with all the uncertainty quantified, of course. Ideally, still a little bit under discussion, we will also provide a routine to do the opposite, One thing which is not mentioned there is that we are now also thinking of generating another strand of level 1C products mapped on a hierarchical grid like those used by the Sentinel-2 family and Sentinel-2 Next Generation, which should make some applications easier for the users. So we will have also this gridded level 1C product on a hierarchical grid compatible with Sentinel-2. And we are always inviting everyone to think about this combination of AOLC and ASLSTR as a super instrument. By the way, AOLC will also have a very improved resolution to 150 meters, so that we will see things in much more detail. A nice view of the Agulhas here with the two instruments on the Sentinel-3 at the moment, ATSR, sorry, no, that's MVSAT, ATSR and MERIS from Ian Robinson's book, and you can see the different detail and the synergies that are possible from the two. In terms of the status of the mission, we are now in phase A, which will be concluded this summer with a preliminary requirements review. So we will check the preliminary version of the requirement to establish that we are good to go to the next phase. And this review will last throughout the summer. Ideally, we then move to phase B1, where we start looking at costs and design in more detail. The launch is still planned for Sentinel-3 NGO-A in 2034, following a couple of years later by S3 NGO-B. On the science side, we've got a mission advisory group in place since the start of phase A. We have regular meetings. Some of you in this room are part of that. We had these science support studies, including the one for ASLSTR, for the consolidation of scientific requirements that are being concluded. We had a synergy workshop last year, which was also very useful in establishing the rationale and the ideas to exploit the synergy of the two instruments on board. And we are planning to release the first public version of the requirements, mission requirement document in September, coincident with the PRR. So this September, we should really like to have all those numbers a bit more consolidated and fully released. I'll conclude just with this summary. Yes, this is my summary slide, which again tells you about Sentinel-3 NGO and this idea that you should take continuity for granted, but we are trying to do the best to have enhanced continuity to go further. And the important thing for ASLSTR are highlighted in yellow in this slide. So once again, a resolution of 500 meters for all channels, and in fact, for the solar channels, we are targeting 250 meters. 3 additional bands, and the one at 8.7 micron is particularly useful for the nadir-only daytime sea surface temperature estimation. And we will target to improve the synergy with AOLC. So the idea is that these will continue to be the reference mission for sea surface temperature and land surface temperature. And when I see, again, I've got sea surface temperature there, but we should rather say aquatic surface temperature, because we will target much better even the coasts with the improved resolution. And we will see certainly big lakes, even the largest rivers. So we will also use it for inland waters. Okay.
Thank you for the nice outlook for the future. So we are looking forward for this. Any quick questions, or we have maybe 2 minutes? Yeah, Leah.
Just a small question, curiosity, Paolo. I saw that you showed that the optical and temporal part is split with respect to altimeter part. Since I was in the team of design several Sentinel-3, driven by Jan Robinson, when we wrote the roadmap of the operational oceanography, the idea to have all the sensors in the same satellite as a real objective to contemporary measurements. So I'm curious why now we go back to this idea and separate, but this is only for the other part. I think these improvements are very important for both OceanColor and SST, but just a curiosity.
Thank you very much, Rosalia. And it's a very legitimate questions that I'm glad to try and answer. I think there was a strong point 20 or 25 years ago in having everything together so that we could minimize that component of the uncertainty deriving from having things on different platforms, so not having an optimized co-location in time and space of the sampling from all the different instruments. So with the progress of the discipline and the fact that we reduce the uncertainty in the uncertainty of the measurements, the uncertainty in the mapping, the geometric uncertainties, and also our knowledge of the processes that now allow us to interpret what we get from the different satellites at a higher level of knowledge than it was possible 25 years ago. I think now it is the time that we can, sort of break this chain between the topography component and the optical component of the mission, because we know that, with the improved modeling, with the higher complexity of modeling and the improvement in the assimilation schemes, we can then bring things together still without the need of having them exactly collocated in space and time. Is that a good answer?
I don't remember how many times in discussion of this, so I understand what is this.
But I agree. I think again, 20 or 25 years ago, I think it was pretty legitimate, and we can only be grateful that we had the possibility of having Sentinel-3 as it is at the moment and exploiting the observations. But now we are in the position that, based on the knowledge that we've acquired, that we can move further.
Thank you. So our next speaker is Robin Ekelund from EUMETSAT. Will say about CMERS towards physically consistent Copernicus image microwave radiometer level 2 products for the global ocean and atmosphere. Please.
Thank you, Igor. So yeah, my name is Robin Ekelund. I'm working at EUMETSAT. First of all, I would like to give my thanks to GHRSST and DMI for organizing this excellent workshop and for inviting me to speak here today. So to give you a bit of background on me, because I'm also very new to the GHRSST community, I'm working with the microwave imaging team at EUMETSAT, where we are developing level 1 and level 2 products for the microwave imagers under our umbrella, such as the microwave imager. So in that sense, I'm quite new to the ocean surface and the sea surface temperature. So please bear with me, and I appreciate any feedback and help in our work. So yeah, so in 2023, I started working on the level 2 product development for the Copernicus imaging microwave radiometer. So in short, CMER. There's already been a couple of talks that has been about CMER, and I think for many of you, the benefits of the mission is quite clear. So I will just give you the overview of the mission. It's a Copernicus Sentinel expansion mission. So essentially, it's designed to address EU policy, in this specific case, the EU Polar Arctic policy, and also to address gaps in the Copernicus space component. And it's also designed to cover a set of key climate variables as listed here. And EUMETSAT are then responsible for the production of global ocean and atmospheric products, while ESA, our partner in this development, is responsible for the operations of the satellite and for the development of the level 1 and the level 2 of polar and land products. And also to give you a bit of overview of the primary objectives and the secondary objectives of the mission. So first of all, it's designed to provide high spatial resolution microwave imaging radiometer, and to deliver products with global coverage and sub-daily revisits in the polar regions and adjacent seas. And there's a focus here towards polar products such as sea ice concentration and sea surface temperature, etc. But also to maintain L-band and AMSR-like observations continuity in the polar regions. And for the secondary objectives, we also have the global ocean and atmospheric products, as mentioned. So that's under EUMETSAT responsibility. And then the land and other polar products that are under ESA responsibility. So yeah, just to show you a bit more detailed view of the SIMR system and the timeline of the mission. So SIMR is basically composed of one dedicated platform, as you can see to the left, and with a mounted conically scanning radiometer. As you can see, we have an antenna boom and a large deployable reflector subsystem that will be folded during launch and then deployed during space. And yeah, and the reason why we have this huge antenna, for those who are not so familiar with microwave remote sensing, is to achieve this very high resolution microwave observations. Of course, not high in comparison to IR measurements, but still. And regarding the timeline, so the first satellites, SIMR-A, is to be launch ready in 2029. That's the current assumption, with a nominal lifetime of 7.5 years, including commissioning. And then for the second satellite, SIMR-B, in 2035. And there's also an option with a third satellite in case the need is identified at a later stage. And there's also going to be a fuel reserve that allows for extension if needed. Yeah, so to give an overview of the specifications, so one way of describing the sensor is basically like a combination of SMAP, but also of AMSR2. So we have 5 bands ranging from the L to Ka, so from 1.4 gigahertz up to 37 gigahertz. So at the lower band, we have the salinity sensitive channel at L, and then C and X, we have sensitivity to sea surface winds and sea surface temperature, with the upper bands being more sensitive towards water vapor, clouds, and rain. So this is what's quite nice with this mission, is that we have this range of parameters, especially for salinity. We haven't really had a good microwave mission with this kind of width in sensitivity. Also of interest is that we have, it will measure the full polarization. So all 4 Stokes parameters will be retrieved, which is very useful for winds. And also to mention is that we have a swath width of 1,900 kilometers. I think Simon's presentation also showed a quite nice plot on the global coverage and revisit times that are quite good with the Simmer. And to the right, you also highlight here that it's going to be a sun-synchronous orbit in the dawn dusk, so an equatorial crossing time at 6 a.m. descending. And also to highlight here to the bottom right here is that it's conically scanning, so you get the full circular view. Basically, you will get the fore and aft view on each observation of the ground. So this, especially for sea surface temperature, this will help to reduce noise, for example. So yes, and this is just, yeah, the video isn't working, unfortunately. But anyway, so yes, so at EUMETSAT, we are then developing the global ocean and atmospheric products, as mentioned, and this is a suite of 6 products. So of course, we have a sea surface temperature that have a threshold spatial resolution or requirement of 15 kilometers. And for the other surface parameters, we have the salinity, ocean surface wind vector, and then for the atmosphere, we will also be able to retrieve precipitation rate, liquid water path, and the total column water vapor. And bear also notice here that we have different spatial resolutions for the different products due to the varying sensitivity of the channels. Yeah, so this is really the nice thing, as I mentioned with Simmer, that we will have this suite of variables derived or retrieved from a single instrument. And some other information is that it's going to be near real time, 3 hours, but also with a non-time critical product. And of course, it's in the requirements that it's going to be a GRIST data specification formatted product. This is in the requirements. And in addition, we are, well, let us say at this stage, the working assumption is NetCDF4 or similar. But of course, considering the discussion during GRIST, for example, on cloud-based formats, this is still this is something we are, of course, taking into consideration, considering the different user needs. And yeah, to mention also is that we are retrieving the subskin temperature because that's what microwaves are sensitive to. But yeah, as Anne was mentioning in her presentation on Monday, there are some we are working on a diurnal model to harmonize the data sets for validation. So the products that we are that I'm mentioning here is currently being developed by Stellus and Ocean Data Lab in collaboration with Thomas Meissner from Remote Sensing Systems. And what we are, the basic idea at this stage is essentially, thank you, a optimal estimation scheme. So using, I mean, basically a 1D-var method, but considering that we have the multiple resolutions for the products, we're going to have like a cascading scheme where we first retrieve the low resolution products. That is the salinity that can then be fed into the mid resolution and then further to the high resolution. So just to give you the quick overview, but I'm happy to talk more about this with you offline. And they will also produce some test data sets. So we have 5 scenes combining CMMs and ERA5 products. And they will also be co-located with SMAP and WINSAT observations for verification. So this is just to give you a snapshot or to showcase what Stellus and Ocean Data Lab has been producing so far for the test data. So you see This is basically covering the Irma hurricane in 2017. And you can see, for example, to the top left, you see sea surface temperature, subskin, we have salinity, we have the wind fields, and also the cloud liquid water content and precipitation rate. And based on this, they have done simulations to get the top of the atmosphere brightness temperature, and you can quite nicely see the different signals from the geophysical parameters. So, for example, in the L band to the left, we see the salinity, and in the middle, you can see the sea surface temperature quite nicely, but also the wind fields, especially here in the eye of the storms here. Yeah, and this is the upper band, so Ku and Ka, where we have more sensitivity to the liquid and precipitation. And I think another presentation already showed this graph, but it's just to showcase the higher spatial resolution of the of SIMR compared to the similar instruments such as AMSR2. So you see here in the C band, we have a quite nice, nicely sized footprint of 10x20 compared to the AMSR2 footprint of 35 times 60 kilometers. So yeah, and also to mention, we have some, the orbit is synced or arranged so that we will have collocation 10 minutes at the poles with the METOP SG satellite as well. Just to mention, there are some scientific challenges, of course. Just to mention here is that the footprint configuration is quite complicated, and this will require this is a bit challenging for the resampling from level 1 to level 2, but also the level 2 will require a bit of pre-processing in terms of varying contamination from the, for example, the galactic glint into the main beam reflected from the ocean surface. So to conclude, Copernicus imaging microradiometer is fully polarimetric at all bands. We will have the 4.5 view. We launched in 2029. We will retrieve a level 2 product with using a self-consistent optimal estimation scheme, which includes the sea surface temperature, subskin, and then we have the 5 other products such as salinity, ocean wind vector, and the atmospheric variables as well. And regarding the validation, I will refer to Anne's presentation on Monday. So basically, we will utilize and expand the existing framework that Anne and Igor's teams already have in place. So yeah, and just to conclude, I would like to thank Copernicus, as they are the funders of this, and also ESA, that are our partner developer in this mission. Thank you.
Thank you, Robin. Thank you. Very nice. We can, I think, continue now with questions for Robin, because we already had some questions before. Yeah, let me know, Andy.
Thanks. Hi, Robin. You mentioned that the resolution and the target resolution of SST was 15 kilometers. And then you said that the scan rate is 7.8 scans a minute. Is that right?
7.8, yes.
So that's about a 50-kilometer separation between the line scans. So how are you going to get 15 kilometers out of that? Or have you got multiple? You've got 4 horns, have you then? Four C-band horns.
So that's a very good question that I should have explained. So you see here the footprint configuration. So the
blue one, the light blue ones are C-band, are they?
Yeah, the C and X are in the field one, so the 4 footprints here. So that's how we get the coverage along track.
Okay, that's fine.
Sorry? Yeah.
Another question?
Thanks for the nice overview. Just a quick question. You mentioned about the level 1 production also at EUMETSAT. Cosima, do you also plan to produce level 1R type products like AMSA2? Like a regridded level 1R type?
I think this is a question more for ESA, but I think they are planning to develop so level 1A, level B, and level C, which would be a resampled or a regridded product.
Okay.
Jakob. John.
So it sounds like your retrieval algorithm has corrections and it might end up being quite complicated at the end of the day. So have you already started on thinking about how you're going to propagate uncertainties through that? Because if you have something with corrections, you need uncertainties on the corrections, and depending on what they're like, some of them will be systematic, some of them will be random, and the propagation could end up being quite complex. So I'm just wondering if uncertainty propagation is already being looked at, because it really should be looked at alongside the retrieval.
Yeah, I mean, I think the uncertainty is handled by the optimal estimation scheme so you basically get the theoretical error covariance matrix.
No, but you need to feed that with proper knowledge of the uncertainties that are going into the data, and there's going to be more than one. And so you have to know how to deal with that.
Okay. Yeah, thank you for a comment. I would be happy to. I can't really.
Okay, no, that's fine if you don't know.
Jakob.
Yeah, thanks, Robin, for a nice presentation. I was wondering, can you confirm that it's a level 2P product in the sort of instrument geometry that will be available for SST? Do you know that? I mean, now you're working on different scales, like 15 kilometers, 5 kilometers, and so on.
I can't really give a good answer to that right now because this is still a decision to be made. So I can tell you that we are. So what I'm presenting here right now is only the retrieval part. We will have a study soon or a ITT release soon for the pre-processing part, which is the Faraday and galactic lint corrections, etc., but also for the resampling part. And one part of this study is to investigate what type of our level 2 grid is most appropriate.
Okay, thanks. I mean, let us know if you want some input from the GRIST user group or the science team on that aspect, because so it's not just within the data producer, but also the users are being heard. And
of course,
when you define the grid.
I mean, any user feedback is very much appreciated in this respect, and I've already got a quite good feedback or inputs on these and other aspects on this.
Thanks.
Okay. No questions now, not online. Maybe some questions for Paolo on ASLSTR. It's not easy to pronounce, but with time. Jakob.
Yeah, maybe. Okay, one question for you, Paolo. I mean, you're just in phase 0 now, right? I mean, you're in phase 0 for this
phase A.
Yeah, phase A. Sorry, yeah.
In the phase A.
So, but you already determined that it's going to be an ASLSTR instrument. I mean, normally it's like, isn't it up to the industry to come up with a suggestion for an instrument that can fit the mission requirements?
I mean, there have been slightly different architecture being proposed earlier on in phase 0 and so on. I think in the end, what really won is the strong requirement for continuing the climate quality SST measurements that really meant that what our lovely pioneers back at Raleigh 40 years ago had designed was still, very, very much the same, the best architecture. I don't know, maybe Chris, whether you've got any comments. But in the end, you cannot do anything better than what we have with the conical scanner, providing a dual view with the calibration at every scan with the black bodies. Is really a winning design.
Okay, thanks. So that will not change, even though it's early in the mission. So that's good to hear. Thanks.
Okay, I have maybe just one quick point to Paolo. So I also asked you before. So for now we are designing something for 2034, 36. Considering technology is advancing so fast with AI, are we prepared to include all the expected changes in the future, or maybe prepare with technology, or what we can prepare to be more resilient for all the changes that are coming?
It is a challenge which we have to face pragmatically. If I can tell you a little sort of funny thing, is that originally there was someone that had come to us saying that we should do like the first generation of Sentinels, so that I should be sitting at my age writing down the requirement, or coordinating the writing down of the requirements of 4 satellites lasting the 2050s and 2060s. And sorry, I thought personally, no, there was too much. So I pushed back on that to say, no, sorry, we are designing for 2, because already, when we will launch the field, especially in terms of algorithms, the use of machine learning and so on, will have progressed so much that. And I've asked also our experts, how can I account for having artificial intelligence on board to some extent that will allow us to optimize things. On a satellite, is difficult to retain that very high flexibility of rewiring many things. So the very pragmatic approach that we are trying to take at the moment is to bring down all the information that we can afford to bring down. So have a very robust and high capacity downlinks, and then you apply whatever you want on the ground to do your calculation and tricks and optimization. And it's quite a lot to bring down, because I didn't mention in my presentation before, but for AOLG, we are thinking about trying to bring down more than 400 channels of 1.25 microns. So it would be essentially hyperspectral, full continuum spectrum, a very, very high spectral resolution from 380 to almost 1,000 or past 1,000 microns. So it is a lot of information, but I don't think we've got the, how can I say, I don't think we've got the confidence that the AI techniques are so well established and so mature. That's the word that you would want absolutely to implement one, because maybe next year there could be another one which is better. And so we are taking the view at the moment that we'll try to bring down as much as we can, and then we'll apply things in the ground. But feedback is welcome. If some of you thinks otherwise, we are happy to discuss.
Thank you. Thank you. Maybe, we have time for coffee. I know we had a lot of questions to Cristina before, so maybe we can just close now for the now. And if there are any other talks, other question, please discuss during the coffee session. So we are now we are starting at in half an hour. Quarter two.
Mediterranean friends talking. Questions to talk about, very disciplined questions.
Sorry.
Sorry?